Dealing with numbers in chemistry. We're going to talk about Sig Figs, we're going to talk about rounding, scientific notation, a little bit on units, and then trying to get an idea of how we'd actually perceive these numbers and really that we can't. So first off, involving Sig Figs, the point behind significant digits is that whenever we have a measured value, which we do in science, we're dealing with normally real numbers, they're actually measured from something, there's always going to be a certain amount of uncertainty with any measurement. It's always going to be off by some amount. So the precision of whatever measurement you take is going to be communicated by the number of digits you have in your answer. So if you know that you weigh 160 pounds, that has a certain amount of precision to it. If you know you weigh 160.0072 pounds, that would have more precision to it. So Sig Figs are a way of communicating the amount of information you have in your measurement, the precision of the measurement itself. So we have to make sure that when we're writing numbers, we are communicating the right amount of precision. You can't just make up precision. It's going to be based on whatever measurement you've actually made. If you've made a very precise measurement, you can put lots of digits. If you've made an imprecise measurement, then you put very few digits. So dealing with significant digits is our way of communicating the correct amount of precision a measurement has. Counted values, if you're just counting things, you're not actually measuring how many there are, you're simply counting them. And so counted numbers have an infinite amount of precision. They are exactly precise. So we don't have to worry about significant digits for counted values, but anytime we have a measured value, you do need to worry about proper significant digits. So what significant digits are? These are the numbers that you have in your measurement, and essentially they carry information about how precise that measurement is. Sometimes they're called significant digits or significant figures, Sig Figs, Sig Figs, whatever you want to call them. So first thing is that when we're writing down a measurement, writing down a measured value, any non-zero digits count as being significant. So if you have a 1 or a 2 or a 3, those digits themselves will always be significant. If they're written down, they count as being significant. Zeros that are between non-zero numbers are also going to be counted as being significant. So if you had 101 or 2.05, this here would have 3 Sig Figs because the 2 counts as significant, the 0 counts as significant, and the 5 counts as significant. Any zeros in the middle of a measurement count as being significant. Leading zeros are not significant. So if you have a certain measurement, like this one here, those zeros at the front do not contain any information about the precision of the measurement. They can give you the scale of the measurement if you're talking about a small number, but they will not carry any information about the measurement itself. So leading zeros do not count as being significant. Trailing zeros do count as being significant. So if you know, so you take a particular measurement and we get 0.00503, it's only going to be 3 significant digits. The leading zeros don't count as significant, but the 5, the 0, and the 3 all count as significant. If we actually took another measurement and we were more precise, we could end up with 5030 at the end of it. And again, the leading zeros tell us the size of the measurement, but they don't communicate anything about its precision. But if you write this 0 at the end here, it is telling you you know exactly what it is. Because before we wrote it, it could be 0, that's not 0, 0, or it could be a 1, or it could be a 2, or it could be a 3, or it could be a 4. All of those could have been what the next value would be, but without writing it, you have no idea. So when we go to write that measurement more precisely, if we happen to write a 0 there, that means we actually know that it is 0. It's not a 1 or a 4 or a 2 or a 3. It is exactly a 0 there. So we are communicating a certain amount of precision by writing that 0 there. Therefore, trailing zeros count as significant. And here's, again, the same number. And when you look at these guys, you'd say, oh, these numbers are all the same. And in terms of quantity, yes, they are the same. But in terms of precision, we know this bottom number here to a more precise value. We know that these final digits are exactly 0 and 0, and not like a 4 and a 2. or something like that. So these count as significant because they communicate information about the precision of the measurement. Now, in chemistry, we tend not to do estimated values. In physics, you may be more likely to do this. And so as long as it's a measured value, if you're writing that 0, it will be significant. So we would assume if you got a question that had 150 milliliters in it, this trailing 0 we would assume would be significant, though the proper way to fully communicate that it is significant is by putting a little decimal after it, and then you know for sure that that 0 is significant. Because in physics, sometimes they do estimate things and they say, okay, 150, whatever it was, galaxies or something, and that estimated value, that 0 would not count. Chemistry, we tend not to do that, but if you don't want to avoid having the argument, put a little decimal there, and then it will for sure say that that trailing 0 on the left-hand side of the decimal is significant because you put a decimal there showing that it is. Rounding. So when we have to communicate our answers to a certain level of precision, often we're going to have to round them. You do the math in your calculator, you get a big number, you've got to round it off to the proper number of significant digits because you can't answer in more precision than you have measured in the beginning. So we're going to have to round off the correct precision digits, the ones that we are saying that the answer is too precise, more precise than it actually is. So when we go to round this, you guys know the rounding rules, I'd imagine, as you learned them in grade school. If the last digit to be kept is followed by a number that is less than 5, you drop it. So for example, if you had this one here, and let's say we had to round it to 3 significant digits, and we'll talk about why you would have to do that in a minute, but essentially you only have 3 significant digits of precision, so we've got to round this off to 3 digits. Now this number, the first one to be cut off, is a 4, and that is less than a 5. So essentially we would just cut those off there, and we would have 2.85 as our answer. That would be it to 3 significant digits, rounding that 4 down to gone and 2.85. If the last digit is greater than 5, then we increase the preceding digit by 1. So for example, if we had this as our measurement and we had to, because of the measurements that went into getting this number, we had to cut it down to 2 significant digits. Remember, the leading zeros don't count, so we'd have to cut it down to 2 significant digits. But we can see that the first one to be cut off is larger than 5, and therefore we're going to round that 8 up to a 9. And we'd get 0.039. And again, that is just 2 significant digits, and we rounded it off because of that. So those are the obvious ones. The one that sometimes is neglected is that, well, what happens if the number to be rounded off is a 5? And if it is a 5 that is being cut off, then that's right in the middle. So you don't want to do the same thing each time. Often we're told just round up. But then you'd sort of be skewing your data upwards all the time when you did that. So what you want to do is you want to round up half the time, round down half the time. And how that works is if the preceding digit to the 5 is odd, then you're going to stick to the rounding up rule. But if it's even, you're going to, I shouldn't say round down, you're going to leave it alone. You're not going to round it up. And zeros are considered even. So essentially the basic rule is when dealing with 5s, round the preceding digit to even, or if it is even, leave it. So for example, if these numbers here at the bottom had to be rounded to 4 significant digits, each one selected so that it has a 5 there. So the 5 is being cut off, and we're not going to round up every time. We're going to round to even every time. So 24.235 is going to become, we're going to round to even, 24.24, right? Because the 3 is odd, so we're going to round it up to even. Now this next one here, again, we're cutting off the 5. We've got a 2 in front of it, which is already even. So we're just going to leave it as that to get to our 4 significant digits. And the last one here, again, the 5, we're going to round to even. 0 is considered even. And so we're going to leave that at 92.00. Now, the reason why you'd want to do this is because here's a quick example as to why you would want to round up half the time and down half the time. Otherwise, you'll end up with a skew of your data towards the high side because you're rounding up every single time. So let's use this as a quick example as to why we do this. So imagine you borrowed some money from a friend over the course of 4 days. So first day was $450, the next day was $350, the next day was $550, the next day was $250. When it comes time to pay them back, you only have loonies, so you're going to have to pay them in a dollar denomination. So if you were to count these dollar denominated loans and you round it up each time, notice I've chosen fives here, very cherry-picked numbers to give you this point, hopefully clearly. You would say, okay, well, day one, that's $4.5. So if I round up, if we actually figure out the actual amount we owed them would be $16. So if we rounded up, if we rounded fives up all of the time, then you'd have $5, $4, $6, and $3, which means you'd be paying back $18. However, if you round to even each day, look how nicely those numbers work out, the 450 would round to 4, the 350 would round to 4, the 550 would round to 6, and the 250 would round to 2. And so you actually end up with something that is closer to the actual value. If you round up every single time, it skews your numbers higher than they should be. Almost never really a problem, but if you have large data sets, it could add up. Calculation with SigDig. So now that we know what is significant, when we go to do work with numbers, we can factor in their significant digits in determining the right precision to have in our answers. So when we're multiplying and dividing, which generally tends to be what we're doing in chemistry, the answer is going to have the same number of SigDigs as the least precise measurement, or the measurement with the fewest SigDigs. Another way of saying the least precise measurement. So you look at all the numbers you put into your calculation, whichever one is least precise, find out how many digits, significant digits it has, and then you're going to have that same number in your answer. So your answer has the same precision as the least precise measurement. So if you had 2 centimeters, and that's 2 significant digits, 1.56 centimeters, which is actually 3 SigDigs. So you're multiplying 2 different numbers there. One of them is more precise and one of them is less precise. Your answer is going to have the same number of significant digits as your least precise measurement. So when you go to multiply these together, you want to write your answer down in 2 significant digits because that's the amount of significant digits that is in the least precise measurement. When you're adding and subtracting, we tend not to do a lot of this, but for molar masses we'll be doing it. It is going to be actually the number of decimal places. Whichever one has the fewest number of decimal places, that's the amount of decimal places you're going to be answering in. So if we had, say, 98.321, that has 3 decimal places. This one here has 5 decimal places. And so you'd say, okay, well, this one has the least amount of decimal places. So when I go to do my answer, I'm going to make sure I answer to 3 decimal places when you're adding and subtracting. Again, not as common as multiplying and dividing for chemistry. Quick note on scientific notation. We're often dealing with numbers that are either very small or very large, and so we want to be able to write them in scientific notation to quickly communicate that information. So scientific notation expresses a value as a number with a decimal place after the first digit. So we only ever have 1 digit. If you have a decimal place, we only ever have 1 digit to the left of the decimal place. You can have as many as you want to the right of the decimal place. That's fine. And that will be based on how much significant digits you have. Then what we do is we express it as that number multiplied by 10 to the something as the exponent there, depending on whatever it takes to get it to be its true value. So for example, we could express 183 as 1.83. In order to get 1.83 to actually be equal to 183, we would have to multiply by 10 2 times. Multiply by 10 once, you get 18.3. Multiply by 10 again, you get 183. So we're expressing that number as a digit, decimal place, and then however many digits we need to get to the amount of significant digits it has, and we multiply by 10 to the whatever times it takes to get back to the original number. If we had this large number here, and again, this is an example of seeing a lot of precision here, assuming this is chemistry, and again, you could put a decimal there to be sure that these digits are all significant, but this would be 7.9345000 times 10 to the 7. Small numbers can also be written this, and again, we're using a negative exponent to show that we're essentially dividing by 10, or multiplying by 10 to a negative exponent, same thing as dividing by 10. So if you took 4.7 and you divided it by 10 3 times, you'd be down to 0.0047. So we can express both very large and very small numbers as scientific notation. Make sure you know how to do this on your calculator. You're not writing in times 10. You are probably finding in there an EXP button or an EE button, or sometimes it is its own button that says times 10 on it, but you're not pressing multiply by 10. Make sure you can figure it out for your particular calculator. So 100, again, we're timesing 1 by 10 twice. That's going to give you 100. And then again, 1,000 by 3 times. 4 would give you 10,000, 5, 100,000, 6, 1,000,000. And if you're dividing, again, if you took 1 and divided by 10 once, you get 0.1, 0.01 if you divided by 10 twice, 0.001 if you divided by 10 3 times. So if you look at these ones and you wanted to express them as scientific notation, again, this is 4, but it's been divided by 10. We've essentially moved the decimal 1, 2, 3, 4 times if we wanted to write it as 4. So 4 times 10, and we divided by 10 4 times. So we're going to write that as a -4, and that's going to be our scientific notation of 0.0004 is going to be 4 times 10 to the -4. And again, we only have one significant digit here. So when we write it in scientific notation, you're sticking to that number of significant digits. This one here has 4 significant digits. If we wanted to express it in decimal form, we would have our 6, essentially move the decimal place, find our pen here, 1, 2, 3, 4, 5, 6, to get it written in its scientific notation form. So if we want to go back to the decimal place, we're going to have to move the decimal place this way, 1, 2, 3, 4, 5, 6, until we have our 0.00001248, and so on, and so on, and so on. All right, quick thing about units. Terribly important to keep track of these as you're doing your calculations. You don't get to determine what the unit will be in your answer. The math will determine that. Obviously, you'll have a goal as to what you want it to be, but you need to make sure that the math is going to give you the correct unit at the end of your calculation, not just because you want it, but because the math determines it. So we will tend to be using kilo and mega, milla for sure, sometimes centi, probably never deci. I wouldn't use those too much if you're getting really small, micro or nano. But these are the prefixes to the particular unit itself. So say we're dealing with grams here, not a bad unit. If you had 1,000 of those, it would be a kilogram. If you had 1,000ths of those, of one of those, it would be a milligram. And so we can look at the numerical value and again see how that affects the scientific notation. So if you wanted to, you could express the number in scientific notation, or what you could do is you could use the prefix to avoid having to do that. So if you had 1 kilogram, that would be the same thing as 1 times 10 to the 3 grams. Those would be equal to each other. And so we can switch back and forth between expressing our values, changing the prefixes on the unit, or using scientific notation on the numbers. The SI standard units that we're going to be using, kilogram is the actual standard unit for mass. We're also going to be using Kelvin for temperature, mole a little bit later than that. We tend not to use time too often, but it would be second if we were using anything with rates. And then if we did happen to measure distance for some reason, meters is the SI unit for that. So metric units for masses, again, kilogram, gram, probably never use decigram or centigram, but milligram is quite often, and microgram if you're doing something particularly small. But kilogram and milligram are going to be more common, or just in grams. We can measure volume using several different means, and so often we're going to be measuring the actual volume of things as well. Graduated cylinder is pretty precise. Volumetric flask will give you a particular volume and only one particular volume, but also very, very precise. Burettes, if you want to have a precise but variable amount of fluid, you can use that to actually measure out a certain amount of volume of fluid quite precisely, and then if you wanted to continue adding it, you could do it, so a variable amount of fluid. Unlike a pipette, which tends to be, again, similar to a volumetric flask, but for smaller amounts, only for a particular amount. So say this one device here, this volumetric pipette, is only going to measure 10 milliliters. It can't do 9 or 11, it's only 10. And then we could have actually micropipettes. Probably not going to be using syringes, but the micropipettes are another way of having a very precise means of delivering volumes. Some things to know as well that comes up a lot. A milliliter of water weighs 1 gram, which means the density of water is 1 gram per 1 milliliter. Handy thing to be able to convert between mass and volume. Again, that only works for water. So knowing that, if you had 1 liter of water, and again, this is a milliliter, so a liter would be thousands of those. So it would weigh 1,000 grams, which would be the same thing as saying 1 kilogram. Last couple of points we want to make is that the numbers that we're using can sometimes be incredibly small. When we're talking about like concentrations of minerals in water, something like that. Incredibly small. We can express the amounts in parts per million, which means if you had 1 million molecules and one of them was this particular molecule, so 1 million molecules of water and one was actually a molecule of, I don't know, chlorine, then that would be parts per million. Or if it's even smaller than that, we can say parts per billion. So this brings up the idea, the concept of the scale of some of the numbers that we're going to be using. So quick thought on how big is a million. If you counted really fast, you might be able to get to like 25, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Let's say that was 10 seconds. Then if you counted for a minute, that should get you to about 150. If you counted for an hour, you could probably get somewhere around 10,000. So you can see where we're going with this. So if you counted for 8 hours with no breaks, you could probably get to 250,000. So therefore, if you spent your days counting, and again, that's sort of a work day schedule, 8 hours a day, you could probably get to 1 million if you counted for about a week, a short week. And so 1 million is a pretty big number when you actually go to count how big a million is. So to basically take you a week of school hours anyways, to actually count to 1 million. So a billion then is obviously bigger than that, but try to think about how big that is. So again, if we're going for 8 hours a day, you're going to have to continue counting for over 20 years to get to a billion. You're looking at 1,000, get 1 week for 1 million. So 1,000 times that, and 1,000 weeks is going to work out to be about 20 years worth of counting. So it's very, very easy to say a billion or to write a billion, but to actually perceive how big that number actually is, very, very difficult to do. So here's one way of thinking about how big that number is. Now a billion, that is 1 times 10. We have 6 would be 1 million, so 1 times 10 to the 9 would be a billion. Now the number that we're going to be using is 1 times 10 to the 23. So if 1 times 10 to the 9 is almost inconceivably large, this number here is going to be very hard to imagine.